So what are the objectives for this workshop? There's quite a few here. I've really bulked it up. It isn't exactly the same as the one that I did a few weeks ago, but because I've got more time, I just thought I'd put a few more things in there. So provide examples of GeoGebra applets through discussing pedagogy. Haven't discussed pedagogy yet, but I've shown a few examples of GeoGebra applets. To develop the case for why GeoGebra is a great tool for dialogic teaching and confirming conjectures. I only heard this term a few months ago by reading Danny Brown's blog, squeaktime.com. He had the definition of a dialogic teacher on there, and it really resonated with me when I saw it, because I think that dialogic teaching is a great way of teaching, and I think GeoGebra is a great tool to facilitate that type of teaching. Obviously, I want to provide some technical tips on sliders, buttons, checkboxes, and basic commands. I might split this workshop up into a few sections though, so I might do maybe 3 videos instead of just one. We'll see how it goes. And then I also want to talk about what makes a good learning experience with GeoGebra. So important to talk about that pedagogy. And then the last one there, do you need to be able to make great applets to get students using it effectively? We'll talk about that as well. First of all then, what is dialogic teaching, if you've not heard of it? Well, you can go on to squeaktime.com to find the definition for it. I think I got this directly from squeaktime.com. But here it gives the kind of the general, I guess, not axioms of dialogic teaching, but the general rules of it. So it's collective. Teachers and students address learning tasks together, whether as a group or as a class. It's reciprocal. Teachers and students listen to each other, share ideas, and consider alternative viewpoints. Supportive. Students articulate their ideas freely, without fear of embarrassment over wrong answers, and they help each other to reach common understandings. Cumulative. Teachers and students build on their own and each other's ideas and chain them into coherent lines of thinking and inquiry. Purposeful. Teachers plan and steer classroom talk with specific educational goals in mind. So it's not just complete open inquiry, but I guess it could be, and you steer it, but I guess then the definition of open inquiry is that you wouldn't want to steer in any direction. But dialogic teaching is trying to steer classroom talk with specific educational goal in mind. And obviously you're not always going to want to do that. At times you're going to want some open inquiry, but I tend to find that I have a specific goal in mind and I'm trying to steer and facilitate discussion that way. And I find that GeoGebra is just a tool that helps me with the entire idea of dialogic teaching and the implementation of it. So I want to provide a few examples of that. I've got it at the top here. So using a GeoGebra applet to provide extra evidence for a student or class conjecture. So when students are discussing, along with you, kind of the why something's going on or making a conjecture about something, I find that GeoGebra can help provide extra evidence, can confirm a conjecture, kind of like replicating an experiment in science, just providing more data to give you a better idea of what's going on. So I want to give a few examples of how you could fit this idea into certain classes. And the first one is with multiplying fractions. So how could you understand multiplying fractions with GeoGebra? Well, first of all, there's no way that I'd start with any type of applet. I tend to start with folding paper. So this square here, 1 unit by 1 unit, I would cut that out or get students to cut it out. And then when you fold it up, then you folded it in half. So here is the halfway line. And then you fold it again the other way, you folded it in half again. So here you've got a half and a half. Now we know that 1 times 1, the entire square, is 1 unit squared. So a half times a half is of course just a quarter of that 1, which is a quarter. So a half times a half is a quarter, and students can see that proportion when they're folding up the square paper. They can see that a half times a half is equal to a quarter, this proportion here. And then you can go on and ask, well, what would then a quarter times a quarter be? Try and visualise that in your head without folding any paper. And certain students are able to do that, and able to explain their understanding to others. And then, of course, you can just get them to fold it and show that it would be 1/16. It would be the proportion 1/16. So a quarter times a quarter is 1/16. So you've got that. And then, instead of folding the paper now, we don't want the paper. Maybe you do many more examples than this, but if you want a good pace to the lesson, you might not. Depends on the students that you're working with. But an eighth times an eighth, then, let's not fold the paper anymore because it starts to get pretty awkward. And think about the folding just as a square that's broken up into 8 parts along the width and 8 parts along the height. So what's an 8 times an eighth? Well, it's just this small proportion here. It's 1 out of 64. And here then is where I might bring in an applet. It might take a bit of time to load. So here's an applet that I put together a while back. I'm just going to change the question because that one's a bit too easy. So 3/4 times 4/8. We've not just got unit fractions now. So again, I'd probably get students thinking about how they then split up this square. And someone will say, well, you split up the height into quarters and you split up the width into eighths. And now we actually want 3/4 up and 4/8 across. So what's that proportion? Well, it's actually going to be 12 out of 32 in total. And at this point, you often get students putting their hand up and saying, I've got a better way to do it, I've got a quicker way to do it. And they realise that you can simply multiply the numerators and multiply the denominators. And you obviously try to curb that and try to get everyone to see it with more and more data and have it all written on the board with just more than three data points. But you can obviously have so many more data points and confirm your conjecture by using a Geogebra applet. As another example, if you're looking at the volumes of pyramids and prisms, then here's a square-based pyramid and a square-based prism, and you might ask the students what those two shapes, 3D shapes, have in common. And obviously they'd say that they have the same perpendicular height and the same base. So I wonder if they have anything in common in terms of their volumes, in which case you're going to start getting conjectures. So you're going to start getting, well, if I turn that pyramid upside down, fill it up with water, and then fill the prism up, how many times will it fill up? And a lot of people say twice. Sometimes students say 2.5 times. Sometimes people say 3. I don't often find that they say 3 times. Often it's 2. But then you might show a video. This video I just got straight off YouTube. I've got the link down there. Show a video of an example of this, of someone actually pouring in the liquid. If you have these shapes in your school, or if you have a way of making them, then of course you'd probably do it with the students to really get some hands-on learning going on. But then, so you can see that we're playing out this scenario and trying to confirm our original conjecture. Is it going to be 2 times? Well, just after that first pour, I'm starting to think, maybe it's not going to be 2 times, maybe it's going to be 2.5. And obviously, it turned out to be 3 times. But again, the problem with that is that we've only got one example of one pyramid and the surrounding prism. So that's just not good enough for mathematics. And obviously, having lots and lots of data isn't good enough for mathematics. But at school-based level, when you're trying to really hone in on certain concepts, and sometimes you just cannot justify everything. So we just want more data to confirm our conjecture. And that's where Geogebra comes in. So I've got an applet here where I've got a triangular-based pyramid. So not just talking about square-based pyramids anymore, but a triangular-based pyramid with the surrounding prism. Same base and same perpendicular height. And you can see here that Geogebra works out the volumes instantly, and the conjecture's been confirmed with another piece of data, because the pyramid is, the prism is 3 times bigger in volume than the pyramid. And I can, change. Oh, why isn't that? Oh, that's a shame. Not quite sure what's happened there. Let me try and open that again and see what happens. Sorry about this. There we go. Don't know what happened there. But you can see that you can have lots of different pyramids, not just a square-based pyramid, and every time it looks like the volume of the prism is 3 times bigger than the volume of the pyramid. No matter what the perpendicular height, oh, we've got a problem, what's happened there? Of course, hopefully a student will realise that they're simply just rounding errors in GeoGebra, and it's still 3 times bigger. But just to confirm with the square-based pyramid, and just to change that to a more... So now it's looking better. It's now looking more like 3 times bigger. So we can confirm that we can confirm that almost with a cone as well, and confirm that the volume of the prism is definitely 3 times bigger than the volume of the pyramid in lots and lots of cases. It's not been proved, but we are confirming our conjectures, which is often good enough with certain concepts at school-based level, I think. So there's just 2 examples of dialogic teaching with GeoGebra, with making conjectures and confirming them with more and more data quickly on GeoGebra. And I've got lots more examples of doing things like this on my blog. So the first one, for example, of course, you'd probably make some circles and get some string and measure them, maybe some really big ones on the floor, and to show this connection between that should say diameter, I think, not diagonal, just change that, the diameter of a circle and the circumference of a circle. But then you've only done 3 examples. What if you do the 10th example and it's no good, it doesn't work anymore? We haven't got this connection of pi between the diameter and the circumference. And I think that's, again, where GeoGebra comes in. You can generate lots and lots of data to confirm your conjecture. And the same with other applets here. Again, they're all in the GeoGebra section of my blog, so you can take a look at them. Obviously, there's so many more. I'm just showing you some that have really worked well for me. Okay, I think I'm going to stop it there, just to make sure the video is still playing and all good. And I'm going to start with the next section, with the next video. So thanks for listening to the first section.